Hello everyone, welcome back to the Black Hole Project. In this video we'll concern ourselves with one of the most important visual elements of a black hole, the accretion disk. It is a disk of hot gas surrounding a black hole, and together with the bending of light, it creates this iconic shape of a black hole in science fiction. In this video we'll create one, or at least we'll lay the foundations of creating an accretion disk. Implementing an accretion disk is quite complicated. So in this video we'll do all the mathematics and implement the core parts of the shader, and in the next video we'll do the visual appearance of the disk. As I said, creating an accretion disk is complicated, so this video will be a long one, and mathematically by far the most difficult one of the entire series. The result though is so much worth it. When you face a complex problem like this, it is a good idea to start with the big picture, and try to come up with a plan for a solution, without thinking of the details yet. And with a plan, I mean more like subdividing the problem into smaller subproblems, such that if all of those subproblems are solved, you would have your solution, but without thinking about how to solve those subproblems yet. So let's do just that. We can start by sketching out the geometrical setup. We have our black hole here at the origin, and the plane of the accretion disk, which we'll take to be horizontal to make our life a bit easier. Then we have our camera in some location, and we have a light ray going in some direction. It will be easier to think about a light ray going away from the camera, instead of a light ray coming from somewhere and going into the camera. This ray will then follow some orbit around the black hole, and intersect the disk plane at some point. For now, let's assume the camera is pointed towards the black hole, such that all light rays cross the disk at some point. What we need to find is this intersection point, and we'll need its position in 3D space. Since we assumed the disk plane was horizontal, and the black hole was at the origin, we already know the vertical coordinate to be 0. There we go, 1/3 of the work done. Let's now start to subdivide the problem. First, we can separate finding the 3D position of the intersection point into two separate problems. We need A, the distance of the intersection point to the black hole, and B, its direction from the black hole. We can set aside the direction problem for now. That's going to be one of our subproblems. When we are only interested in the distance from the black hole, we can reduce the problem from 3 dimensions to 2. To see how, consider the angle between the direction of the intersection point and the direction from the black hole to the camera position. When we change the impact parameter of the light ray, this angle stays the same. To see why, picture the plane of the orbit. By definition, the intersection point lies on the intersection line of the orbit plane and the disk plane. So this angle, let's call it phi p for plane angle, can only be dependent on the location of the camera and the orientation of the orbit plane. If we knew phi p, we could rephrase our problem in the orbit plane. Let's use polar coordinates instead of this Cartesian grid, and let's also reorient our view a bit such that the light ray orbit goes to phi equals 0 for r going to infinity. We can denote the camera position as rc phi c, where phi c is no longer representing the position of the camera in the scene, but rather at what position on the light ray orbit the camera is located. Let's also indicate the turning point, which I'll call phi tp. Remember, what we need is this distance, which I'll call rd for r at disk. So this is r at phi equals phi c plus phi b. So if we had a function r of phi and b, we could plug in the value of b for our light ray orbit and phi equal to phi c plus phi p to get rd. This is something we can put into a texture. The last thing we don't know is phi c. We can do the same thing we just did for r. We know phi c is a function of b and rc, so given a value of b and rc, we can calculate phi c. This function is not limited to the camera location, so we can express phi in general as a function of b and r. This is a second texture we'll need to make. In principle, we now have everything, but there's one more thing we can do here. We can make use of the fact that the light ray orbit is symmetrical with respect to the turning points. This means that we can double the resolution of our texture of r phi b by only saving phi up to the turning point. The way we handle this is by checking if phi c plus phi p is greater than phi tp, and if so, return r of this angle instead. This angle is a total angle swept out by the orbit minus phi c plus phi p. The total angle swept out is precisely 2 times phi tp. So if phi c plus phi p is greater than phi tp, we return r at 2 phi tp minus phi c plus phi p, instead of r at phi c plus phi p. That does mean we need to create a third texture, phi tp of b. But the additional resolution of r phi b is totally worth it. Alright, we now have all the subproblems laid out. We need the direction to the intersection point from the black hole, a texture for r phi b, a texture for phi rb, and a texture for phi tp of b. Now we'll go over each of these things and solve them one by one. Let's start with the direction to the intersection point. We can do this neatly with some vector math. We actually only need two things: the camera position, which is this red vector, and the view vector, which is a vector pointing into the direction of the light ray at the position of the camera, so this green vector here. The view vector is a node we have access to in our shader in Unity, so that's neat. What we're looking for is this blue vector. The length of this blue vector doesn't matter, since we're only interested in the direction for now. We know that all three of these vectors are in the orbit plane, so let's look at this in 2D instead of 3D, since that's a bit easier to visualize. Keep in mind though that we're still looking at 3D vectors, we're just looking at them in the orbit plane. Let's give these vectors some names. We'll call the red vector rc, because it's the camera position. We'll call the view vector v, and the blue vector rd, for position in the disk. We want to express rd as a combination of rc and v. There has to exist some linear combination of rc and v that results in rd. In fact, there are infinitely many, because we haven't specified the length of rd. Since we're not interested in the length of rd, we can get rid of this b. In other words, we are looking for the value of a, such that if you multiply rc by a and add v, you get a vector that is parallel to rd. To determine a, think about what defined rd in the first place. The vertical coordinate is 0. Keep in mind that's the vertical coordinate in 3D space, not necessarily the orbit plane we're currently looking in. Unity uses the y-up convention, so we can express that condition as a times the y component of rc plus the y component of v equals 0. And then we can rearrange these terms to get an expression for a. So we have this expression for rd. One final thing we can do is normalize rd such that we have a unit vector in the direction of the intersection point. Alright, let's do the turning point next, because it's relatively straightforward. Back in my first video, we found this expression for the total angle swept out by a light ray. Since the turning point is a halfway point on the orbit, we can just remove this vector too, and we have an expression for the turning point. Now all we need to do is calculate this integral for different values of b. Next, we need to decide which values of b we want to consider. Picking a lower limit is easy. We know a light ray goes into a circular orbit for b equal to the square root of 27. A circular orbit means the turning point is at infinite phi. In our shader we used 5.1962 instead of the square root of 27 to avoid infinite values, so we can do the same here and take 5.1962 as a lower limit on b. We don't really have an upper limit on b. At very large b, light rays just go in straight lines, so phi tp converges to pi over 2. Since phi tp slowly converges to a value, we can just take our x-axis in 1 over b and have a range between 0 and 1 over 5.1962. This way every possible value of b is covered. And we have most of our resolution spent on small values of b, which is where phi tp changes the most. Finally, we need to decide on how to map phi tp to a 2D image. Remember, we have a 1D array of values of phi tp for different values of b, and we want to have a square image of say n by n pixels. What we can do is split this array in pieces of n elements and stack those parts on top of each other. To access element k in the array, we can then access pixel ij, where I is k over n, rounded down, and j is k mod n. Let's take a look at the code for creating the texture. We have the brackets, integrand, and integral functions as usual. Then in this turning point function, we calculate the integral to w1. Then we choose a resolution for the texture. This doesn't have to be very big. For a resolution of 64 by 64, we have 4096 values of b, which is plenty. Then we create an array of values for b, and we calculate the turning points for each value. The first value in this b array is infinite, so we just set the first value of the phi-tp array to pi over 2. Then we just go through each pixel of the texture and assign the corresponding value of phi-tp. As usual, we save the texture, and before we do so, we invert the y-axis. Next up is phi rb. Just like we did in the last video for the deflection angle, we can replace b here with the view angle, since any of the variables r, b, and view angle can be expressed as a function of the other two. That way we can include looking away from the black hole. We're going to implement looking at the disk away from the black hole in a later video, but this way we're already prepared. Just like before, we use a horizontal axis for the view angle, but now ranging from 0 to pi over 2 instead of pi. The vertical axis is again proportional to 1 over r, ranging from 0 to 1 over 3. Calculating the texture is pretty straightforward. For every combination of the view angle and distance, we can calculate b. Then for each value of b, we can integrate the phi dr from r equals infinity to r. The last thing we need to figure out is a texture of r phi b. The reason I do this one last though is because it is by far the most complex one. Here's the problem. Everything we have done thus far has been done using this one equation for the phi dr, which is a function of r and b. But now we need to calculate r from phi. We don't have an equation to do that, and I have been unsuccessful in finding one. So what do we do then? Well, we can work backwards. First off, remember that we're only considering phi between 0 and the turning point. There's a very useful property about r in this range of phi. For increasing phi, r always decreases, and then after the turning point, r always increases for increasing phi. So, for phi between 0 and the turning point, r is a monotonically decreasing function. Now, imagine we have some value of b, and we want to calculate r at phi 0. We don't know how to do this, but imagine we know something more. We also know phi 1 at r1 and phi 2 at r2. And we know that phi 1 is less than phi 0, and phi 2 is greater than phi 0. Since r is a monotonically decreasing function, we therefore know for certain that r at phi 0 must be between r1 and r2. Okay, knowing this, let's take a third r, r3, halfway between r1 and r2, and we calculate phi at that value of r. We'll call that phi 3. Now there are two possibilities. Either phi 3 is less than phi 0, or phi 3 is greater than phi 0. Suppose phi 3 is greater than phi 0. We can then take r1 and r3, and we still know for certain that r at phi 0 must be between those two values. Okay, so let's take a fourth r, r4, halfway between r1 and r3. And we do the same, we calculate phi at r4, and call it phi 4. Suppose now phi 4 is less than phi 0. We now know that r at phi 0 must be between r3 and r4. We can keep on doing this, and you can see that each time the interval in which we know r at phi 0 must be halves in size. So quite quickly, we know r at phi 0 with a very small uncertainty. Once we have reached an uncertainty that we find sufficiently small, however small that may be, we can then say, okay, we know r must be between ri and rj. Let's take r equal to the average of those two values, and we know that within a very small uncertainty this will be correct. This is great and all, but we do need that r1 and r2 to begin with. Luckily, we can quite easily find them. a guaranteed lower limit for r is 3m. So we can start with r2 equal to 3m. We don't really have a guaranteed upper limit like that though, so what we'll do is pick a value, let's say 10m, and calculate phi at this value of r. If this phi is less than phi 0, great, we have our r1. If it is not, it wasn't for nothing, we have found a better value for r2, and we try again, with a larger value of r, say twice our previous guess. We can keep on doing this until we hit a value of r for which the corresponding value of phi is less than phi 0. This way we can calculate r for any given phi and b. To create a texture, we just need to do this for a lot of combinations of phi and b. The only problem is that calculating phi for a single r and b means solving an integral numerically, and we need to do that a bunch of times for every single pixel in the texture. So you can imagine this is computationally very expensive, especially in a language like Python that is not really known for its efficient performance. In any case, for a texture of 512 by 512 pixels, this took a few hours to run. That was acceptable for me, but for any larger texture size, you would need to do this in a more performant language. Before we take a look at the code, we need to decide on the axes of our texture. I had some new ideas for this one. On the horizontal axis we have b, and on the vertical axis we have phi. I again wanted to have the horizontal axis inversely proportional to b, such that we cover up to infinite b and have most of our resolution spent on small values of b. However, we also need to go down to b equal to 0, because we have to be able to look at the disk when it is in front of the black hole. After playing around with functions a bit, I came up with this mapping, which has all the required properties. This factor a is a free parameter. It determines what value of b is at the center of the axis. I took a equal to 20, which means that half of the resolution is spent on values of b below 20, and the other half is spent on values above 20. For the vertical axis, it was difficult at first to decide on a range of phi, because for rays close to the black hole, the turning point is at quite large phi. But on the other hand, if we take a very large range in phi, we waste a lot of the resolution of our texture. And if there's one texture we want to optimize the resolution of, it's definitely this one. But then I had a realization. For a ray that goes very close to the black hole, and thus has its turning point at large phi, the part of the ray that is at large phi is at r very close to 3m. Now, minor spoiler alert for the next video, but the accretion disk doesn't actually go all the way down to r equal to 3m. This means that we don't actually need r for very large phi. Taking phi up to pi is already more than sufficient. There are three edge cases here. X equal to 0, which is infinite b, x equal to 1, which is b equal to 0, and y equal to 0, which is phi equal to 0. Unfortunately, these edge cases do not have a very clear asymptotic behavior, so what I did instead was to not include those in the texture. In most cases this is totally fine to do, and this is one of those. What this means in practice is that we have, for example, the vertical axis from 0 to pi in 513 pixels, and our texture just doesn't include the first row of pixels, corresponding with phi equal to 0. I don't want to go over the code in much detail, but I will point out some key things. For rays with b greater than the square root of 27, we don't go beyond the turning point. So if phi is larger than the turning point, we just set a value in the texture to r at the turning point. For rays with b less than the square root of 27, we don't go below r equal to 3m. So before we start filling in the texture, we calculate at which phi each ray reaches r equal to 3m, and beyond that phi we just fill in 3m. The function getRphi is where the heavy lifting is done. It basically does what we just discussed, but I also added a max number of steps as a safety measure. I used a relative tolerance of 10 to the minus 6, meaning that we consider the interval small enough if the middle of the interval has a value of which the first 6 digits are the same as input phi. Finally, since we have a large range in R, spanning multiple orders of magnitude, I decided to save the texture in log R. This way, the linear interpolation between the pixels in Unity should be a little better. It's finally time to hop into Unity and start working on our shader. The texture settings for phi r view angle and log r phi b are the same as for delta phi b and delta phi view angle, but phi turning point is a bit different. Wrap mode should be set to clamp. Actually, I think I forgot to mention that for the other textures. For all textures, wrap mode should be set to clamp. And also, very importantly, under Advanced, Generate Bitmaps should be disabled for all textures as well. For phi turning point, filter mode should be point. We'll have to do the interpolation ourselves. Max size is 64 and no compression. Let's start by making a few subgraphs. First, phi r view angle. This takes in r, m and the view angle and returns phi. The u-coordinate is then the view angle divided by pi over 2. The v-coordinate is m over r times 3. Then we do the UV pixel center correction and sample the texture. Next up is r phi b. This is similar but slightly more complicated, since we chose not to include the edge cases. Remember, we had this fancy mapping from x to b. We need the inverse mapping to go from b to x. So divide b by m, multiply by 0.05, add 1, and then divide 1 by all of that. Then we need to account for the fact that we don't include the edge cases, which we can do with a remap node. 0 we want to correspond with 1 over 512, and 1 with 1 minus that. For the v-coordinates we had phi ranging from 0 to pi, not including 0. So we take phi, do the same remap trick, but this time we do want 1 to correspond with 1, and then we multiply this by pi. Remember, we chose our texture to be in log r, so we need to do 10 to the power of this texture. On to the turning point. This will take in b and m, and return phi tp, as well as twice phi tp, since that is the total angle swept out by the ray, and we'll need that too. The UVs for the turning point are a bit more complicated. We start by dividing m by b, and multiplying that by 5.1962. Then we multiply by the resolution squared. We now basically have the index in the array of b, except that this index is a float and not an integer. For now, we round it down to make it an integer. Then we can do modulo resolution and divide by the resolution to get the u-coordinates. If we subtract this modulo from the original and divide by the resolution squared, we get the v-coordinates. So here we basically do the same stacking as discussed earlier, but using u and v between 0 and 1, instead of I and j between 0 and n. Then we do the pixel center correction and sample the texture. You might think we're done now, but not quite. Remember that we had a float index here, and we rounded it down? Well, we can do better. We can use the decimal part of the index to interpolate between the pixel we're accessing here and the next one. To get the next pixel, we just need to copy-paste this entire thing, and change this floor to ceiling. Then we lerp between these two, using the decimal part of the index as t. Getting the decimal part of the index is pretty straightforward. We just subtract the rounded down index from the float index. Finally, we need to take care of rays that fall into the black hole. Otherwise they can do some weird things. We can simply set a turning point for all rays with b less than 5.1962 to some large value, like 1000. The last subgraph we need is phi p. This takes in the camera position and the view vector. Here we first calculate RD. So we take the view vector, and before we do anything we need to flip its direction, because the view vector in Unity for some reason is not the direction in which you are looking, but the opposite of that. Then we take the y component, multiply that by -1, and divide it by the y component of the camera position. That gives us A. We then multiply this by the camera position, add that to V, and normalize it. This is RD. To get phi p, we then take the camera position, normalize it, take the dot product with RD, and take the arc cosine. On to the main shader. We start with phi r view angle and phi p, connect everything, and add these two together. That is phi c plus phi p done. Next we have the turning point. For that we need b and a mass. Then if phi c plus phi p is greater than the turning point, we use 2 phi tp minus this angle. And finally we have r phi b, which gives us rd. We can visualize what we currently have by showing a disk for RD between, for example, 6 and 20, and just add it to the environment lights. It seems I've made a couple of mistakes here. In R phi b, this multiply node should be before the remap. And then in phi tp, over here in the subtract nodes, the inputs have to be switched around. And also over here. So now it should work correctly. This shows us already that iconic shape. Alright, we're done for today. In the next video, we'll do the visual appearance of the disk. Thank you for watching, and I hope to see you in the next video.